Hello and welcome back to the channel. In today's video, I'm undervolting and overclocking the AMD Ryzen 7 8700F APU all the way up to 5250 MHz using the ASUS ROG Crosshair X670E Hero motherboard and custom loop water cooling. This will be the fourth Hawk Point APU that I overclock on this channel, following the 8700G, 8600G, and 8500GE. But this 8700F doesn't have integrated graphics, so that's new. Anyway, this will be a relatively short overclocking guide, but I hope you enjoy the video nonetheless. Let's get started. The Ryzen 7 8700F is part of AMD's Zen 4-based Ryzen 8000 desktop processor product line, codenamed Hawk Point. The original Hawk Point processors were introduced on January 8, 2024. The two F SKUs were quietly announced a couple months later at the AMD AI Summit in China. They are similar to their G counterparts, but lack the integrated graphics. The Ryzen 8000 processors come to market in two distinct configurations. The APUs with the Phoenix 1 die have exclusively Zen 4 cores, whereas the APUs with the Phoenix 2 die have a combination of Zen 4 and Zen 4C cores. A lot has been said about the difference between Zen 4 and Zen 4C cores, so I won't regurgitate everything here. But the point is that the core architecture is identical, while Zen 4C cores have a smaller footprint. The benefit is that you get more compute per area, but the trade-off is that you also have higher hotspot temperatures and lower frequencies. The Ryzen 7 8700F has 8 Zen 4 cores with 16 threads. The base frequency is 4.1 GHz and the listed maximum boost frequency is 5 GHz. The TDP is 65 watt and the TJ max is 95 degrees Celsius. In this video, we will cover 3 different overclocking strategies. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. The EFC-SB is a customized version of the original Elmo Labs EasyFan controller. It has the same functions and features as the original EFC, with a tiny improvement here and there. I use the EFC-SB to monitor the ambient temperature, water temperature, and fan duty cycle. I also use the device to map the radiator fan curve to the water temperature. The main takeaway from this configuration is that it gives us a good indication of whether or not the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course we have to check the performance at default settings. The default Precision Boost 2 parameters for the Ryzen 7 8700F are as follows. Here's the benchmark performance at stock. Here are the 3D Mark CPU profile scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4284 MHz with 1.106 volts. The average CPU temperature is 76.3 degrees Celsius. The average CPU package power is 87.8 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4497 MHz with 1.191 volts. The average CPU temperature is 80.7 degrees Celsius. The average CPU package power is 87.8 watts. Of course, we can increase the power consumption headroom by using the Precision Boost Overdrive toolkit, and that's exactly what we'll do in our first overclocking strategy. However, before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply leverage enabling Precision Boost Overdrive and AMD EXPO. With the launch of Zen 3, AMD introduced an improved version of their Precision Boost Overdrive toolkit. They called this Precision Boost Overdrive 2. The PBO2 toolkit allows end users, such as you and I, to adjust some of the parameters governing the Precision Boost frequency boosting algorithm. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. in addition to the overclocking knobs from Zen Plus, PPT, TDC, and EDC, and Zen 2, Boost Override and Scalar, Precision Boost Overdrive 2 also introduces Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. I recently took a deep dive in the Precision Boost Overdrive toolkit in my launch content for the Ryzen 7000 Rafael processors. So have a look at those videos if you want to learn more about Precision Boost Overdrive. In this overclocking strategy, we're just enabling Precision Boost Overdrive, whereas in the following strategies, we'll explore tuning the parameters. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC will help unleash the frequency in multi-threaded workloads. EXPO stands for AMD Extended Profiles for Overclocking, and it's an AMD technology that allows ubiquitous memory overclocking on AMD platforms supporting DDR5 memory. Essentially, it allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. And if your motherboard supports EXPO, then you can enable the higher performance with the click of a single button. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Enabled, then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. Surprisingly, despite increasing the power consumption headroom from 65 watts to 1000 watts, we get little to no performance improvement in most benchmark applications. The geomean performance improvement is plus 1.71%, and we get a maximum improvement of plus 7.70% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4537 MHz with 1.184 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 119.1 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4646 MHz with 1.244 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 110.1 watts. The boost frequency at one active thread is about 5050 MHz, and the average boost frequency gradually trails off to 4723 MHz when all cores are active. All cores can boost to over 5 GHz in single-threaded workloads. In our second overclocking strategy, we tune the processor using the PBO2 toolkit. We will use Fmax Boost Override to overclock and Curve Optimizer to undervolt. In addition, we also do a little bit of optimization of the memory subsystem performance. Fused maximum frequency, or Fmax, is one of the precision boost infrastructure limiters governing the performance of your CPU. Essentially, the Fmax limit determines the maximum allowed operating frequency of all of the cores inside your CPU. Boost Clock Override, or Fmax Override, is one of the overclocker tools available in the PBO2 toolkit. It allows the user to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz in steps of 25 MHz. It's important to note that the Fmax Boost Override only increases the upper ceiling of the VF curve. It doesn't act as a frequency offset. Ultimately, it's still the precision boost algorithm that determines the actual frequency of your CPU cores. Curve Optimizer is a very important new feature of the Precision Boost Overdrive 2 toolkit. Essentially, Curve Optimizer allows end users such as you and I to fine-tune every core's voltage, frequency, temperature curve. The VFT curve is a curve that describes what voltage is required for a given frequency and temperature. Basically, the higher the frequency or the higher the temperature, the higher the voltage that's required. Curve Optimizer adjusts the VFT curve by offsetting the voltages of the factory fused VFT curve. By setting a positive offset, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. You can offset the entire curve by up to 50 steps in a positive or negative direction. Each step represents approximately 5 mV. The typical overclocking approach for AMD Ryzen CPUs is to use a negative curve optimizer. Two things happen when you do that. First, we effectively undervolt the CPU and tell it needs less voltage for a given frequency, and as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the precision boost algorithm to target higher voltages and frequencies. Like in the past, per-core tuning offers a real benefit as it provides some cores with a lot more frequency headroom. The manual tuning process for per-core curve optimization can become quite convoluted because it spans a wide range of workloads, going from light single-threaded workloads all the way up to heavy all-core workloads. I usually spend quite a bit of time per core curve optimization. This time I wanted to use the OCCT stress tool for the curve optimization process. Here's my broad approach. I start off with a negative curve optimizer setting of -15 for each core. Then I use the OCCT CPU stability test with small dataset, extreme mode, and steady load type. I core cycle through each core for 60 seconds with 2 operating threads and AVX2. I increased the negative curve optimizer magnitude by 5 steps for the cores that didn't crash, and I reduced the negative curve optimizer magnitude by 5 steps for the cores that did crash. Once all the cores are dialed in, I run another OCCT, AVX2 and SSE stability test, intending to pass for 30 minutes without any of the cores failing or clock stretching. Again, when a core fails, I reduce the negative curve optimizer magnitude by 5 steps. Once all that's done and everything is stable, I run through the usual benchmark suite and stability tests used in this guide. If there are no instabilities, I consider my curve optimizer settings as stable. On AMD Hawk Point processors, the memory subsystem consists of 3 major parts: the Infinity Fabric, the Unified Memory Controller, and the System Memory. They're more commonly known as the F clock, the U clock, and the M clock. These parts used to be tightly coupled together, but on modern Ryzen processors like the Ryzen 7 8700F, we can tune them independently. There are 2 things I wanted to address when it comes to memory subsystem performance optimization. First, I want to fix the downclocking of the F clock and U clock. Second, I want to run the U clock and M clock in sync. To solve the first problem, we simply enable SoC Uncore OC mode in the AMD Overclocking submenu. This disables all power-saving technologies affecting the clock frequencies of the memory subsystem. To address the second problem, we simply set uClock div1 mode to uClock equals memclock. The memory controller frequency is tied directly to the system memory frequency. It can run either at the same or half its frequency. We run the memory controller frequency in sync with the system memory for this OC strategy. At DDR5 6400, the memory controller frequency is then 3200 MHz. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Switch to the Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the DDR and Infinity Fabric Frequency Timings submenu. Enter the Infinity Fabric Frequency and Dividers submenu. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric Frequency and Dividers submenu. Leave the DDR and Infinity Fabric Frequency Timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set CPU Boost Clock Override to Enabled Positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. For every core, set Curve Optimizer sign to negative. Set Core 0 Curve Optimizer magnitude to 35. Set Core 1, 4, 5, 6, and 7 Curve Optimizer magnitude to 20. Set Core 2 Curve Optimizer magnitude to 25. Set Core 3 Curve Optimizer magnitude to 15. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. enter the SoC Uncore OC mode submenu. Set SoC Uncore OC mode to enabled, then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. Undervolting with Curve Optimizer is an overclocker's best friend for the Ryzen 8000 APUs, as it provides a nice frequency and performance bump. The geomean performance improvement is plus 5.60%, and we get a maximum improvement of plus 14.80% in PY prime. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4644 MHz with 1.158 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 126.3 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4771 MHz with 1.22 volts. The average CPU temperature is 95.1 degrees Celsius. The average CPU package power is 117.2 watts. The boost frequency at one active thread is about 5162 MHz, and the average boost frequency gradually trails off to 4874 MHz when all cores are active. 3 out of 8 cores can boost to over 5.1 GHz in single-threaded workloads. In the third and final overclocking strategy, we're pursuing a manual overclock. Now, originally I had planned to find the maximum stable frequency in my worst case stress test. That's OCCT with AVX2 and all cores enabled. However, I found that the maximum frequency was only 4850 MHz with 1.185 volt, and that would yield benchmark performance lower than stock. So instead, I decided to forego the AVX2 stability requirement and find the maximum overclock for the OCCT SSE workload. But before we jump into the overclocking and the tuning process, let's first have a look at the AMD Hawk Point clocking and voltage topology. The clocking of Hawk Point is similar to other AMD Zen 4 CPUs. The standard Hawk Point platform has a 48 MHz crystal input to the integrated CG-PLL clock generator. The CG-PLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by a frequency ID or FID and divided by a divider ID or DID. Each CCX has its own PLL, with the cores within that CCX running at the same frequency. The effective clock, however, can differ if a core is in a different P state. The SoC PLLs include a wide range of PLLs. The ones most relevant for overclocking are the F clock, U clock, M clock, GFX clock, and IPU clock. AMD Hawk Point's voltage topology is similar to that of previous Ryzen processors. As per usual, the processor relies on an internal and external power supply to generate the processor voltages. There are 4 primary power supplies from the motherboard VRM to the processor. The VDDCR voltage rail provides the external power for 3 internal voltage regulators. VDDCR CPU provides the voltage for the CPU cores within the CCX. The voltage rail can work in either regular or bypass mode, but it is always in bypass mode on Hawk Point. That means the voltage of the cores is always equal to the VDDCR external voltage. VDDCR VDDM provides the voltage for the L2, L3, and if present, the 3D cache on a CCX. The VDDCR GFX voltage rail is not used on the 8700F since the integrated graphics are not present. The VDDCR SoC voltage rail provides the external power for multiple internal voltage regulators on the SoC for various IP blocks, including but not limited to the memory controller, SMU, PSP, and so on. The VDDCR SoC voltage can be set up to 1.3 volt under ambient conditions. The VDDCR miscellaneous voltage rail provides the external power for the internally regulated VDDG voltage rail, which is the voltage supply for the Infinity fabric. The VDD-IO MEM voltage rail provides the external power for the VDDP DDR internal voltage regulator, which is the voltage for the DDR bus signaling or DRAM PHY. On many core processors like Ryzen Threadripper, per CCX tuning can become quite convoluted because there's so many CCXs to tune. However, on this Ryzen 7 8700F, we only have one. So the tuning process will go a lot faster. Our limiting factor will ultimately be the cooling solution, as power consumption increases exponentially with operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we're tuning for. So the first step in our tuning process would be to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. Once we know the maximum voltage, we can tune the CCX. Simply increase the ratio until the application shows signs of instability, then back off. No more, no less. In our case, we reach near TJ max temperatures with a voltage of around 1.25 volt. That gives us sufficient headroom to push the CPU core clock frequency to 5075 MHz. Now that we know the ins and outs of manual tuning of an AMD Ryzen 7 8700F processor, let's jump into the BIOS. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to EXPO 1. Enter the CPU Core Ratio CCX submenu. Set Core VID to 1.25. Set CCX 0 ratio to 50.75. Leave the CPU Core Ratio CCX submenu. Switch to the Advanced menu. Enter the AMD Overclocking submenu and click Accept. Enter the DDR and Infinity Fabric Frequency Timings submenu. Enter the Infinity Fabric Frequency and Dividers submenu. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric Frequency and Dividers submenu. Leave the DDR and Infinity Fabric Frequency Timings submenu. Enter the SLC Uncore OC mode submenu. Set SLC Uncore OC mode to enabled. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. It's unusual for a manual overclock to outperform the stock configuration in single-threaded benchmarks because by enabling OC mode, you forego the high precision boosting frequencies in single-threaded workloads. However, in this case, our manual overclock of 5075 MHz is higher than the stock maximum frequency of 5050 MHz. So we see a performance uplift in all benchmarks, which is pretty neat. The geomean performance improvement is plus 3.90%, and we get a maximum improvement of plus 14.69% in Corona 10. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5075 MHz with 1.199 volts. The average CPU temperature is 88.4 degrees Celsius. The average CPU package power is 121.3 watts. The boost frequency for any number of active threads and all cores is 5075 MHz across the board. Alright, let's wrap this up. The experience of overclocking the Ryzen 7 8700F is very similar to overclocking any of the other Hawk Point APUs. Essentially, the main observation I have for overclocking these CPUs is that the overclocking headroom is pretty limited. I don't know if that's due to the Phoenix microarchitecture or down to the TSMC N4 process technology, but having a maximum overclock of not even 5.1 GHz is pretty limited these days. That's not to say that there's no performance headroom to be found. In fact, with a little bit of precision boost overdrive tuning, so using the if-max boost override and some curve optimization with unlocking the power limit and adding a little bit of AMD EXPO on top of that, you can quite easily get a performance improvement of plus 15% in certain workloads. That's not too shabby. Anyway, that's it for this video. This was also probably the final Hawk Point APU that I'm overclocking on this channel, as I'm looking forward to next generation architectures on the AM5 platform. I want to thank you for watching, and I want to thank the patrons for their continued support. If you have any questions or comments, drop them in the comment section below. If you want to read through my BIOS settings and results, I will also put up a blog post on my website detailing this overclocking guide. And that's it. See you next time.